Welcome to Nuts and Bolts Video 1. In this video, we're going to address central tendency, variance, and normality. Some learning objectives associated with this module in ADM725 are as follows: to describe the conditions leading to normality, quantify deviations from normality, apply basic measures of central tendency and variance to describe standard error, and relate probability with normal distributions through confidence intervals. The reading for this module comes from the field book, chapters 1 and 2, and for this video, the focus is drawn largely from sections 1.6, and then in chapter 2, sections 2.1 to 2.5. So just a quick note on the section listings: when you see those either somewhere in the Canvas course or on one of the videos within the Canvas course, if it says section 1.6, that means all of the subsections within 1.6. So that starts with 1.6.1 and goes through 1.6.5. So I just want to make sure that you understand that that is not simply the first subsection of 1.6. Now I'm going to make a note of another place from another chapter that's not part of the assigned reading, but I think it's something that is illustrative to this topic. So I'll make a note of where to look at in the field book. So when we talk about distribution and normality in statistics, one of the things that we use to help visualize that is the normal curve. And we're going to be getting into some detail with the normal curve during residency week. So I want to make sure that we've got a clear sense of what we're discussing. And we're also going to be revisiting the normal curve when we address two-group analysis using t-tests later in the course. So when we look at a normal curve, we see in the middle that is the normal curve. That means that the variable that we're looking at is normally distributed, that there is some sort of central tendency, and all of the data falls out from that central point of central tendency normally. But then we see in the other two images, so the one on the left shows a negative skew, and the one on the right shows a positive skew. And this for some folks, this can seem a little counterintuitive. So we see on the left-hand image that we get a sense that the main part of the curve is to the right. So we might think that means that that's a positive shift or a positive skew in the distribution, but it's actually the opposite. So if you look at that and it seems counterintuitive to you, I just want to make sure that I provide that little nugget of clarification, that on the left we see that the tail is drawn out, is pulled out more in the negative direction. So it's about the pull of that tail that suggests whether the skew is positive or negative. And those positive and negative skews have some specific names. And so the skew is referred to as kurtosis. And so if something displays negative kurtosis, then that is known as platykurtic. If something is displayed as positive kurtosis, then that is known as kleptokurtic. In reporting, if a distribution is skewed, is generally referenced as being negative or positive in its skewness or in its kurtosis. I'll sometimes see the term kurtosis used in literature, particularly in education journals, which is where I spend my time. But I can't think of a time when I've seen the terms of kleptokurtic or platykurtic being used to describe the skewness or kurtosis. But it's good to be familiar with the terms so that when you do come across them, and Field does use the terms of kleptokurtic and platykurtic in the book. So it's good to have a sense of what those mean. So for this video, I'm borrowing some output that Dr. Lyons generated when he previously taught ADM725. And this data is drawn from some ACT data of 131 high schools from across the Commonwealth of Kentucky. So this image on the screen is a histogram, and a histogram is a graph that depicts the distribution of a particular variable. As you look at this, how would you describe the distribution, thinking about the images of either normal distribution or skew? Jot down your answer, and we'll come back to it for a few minutes, and we'll see if you're right. So what we saw, so I'm going to flip back real quick to the histogram, and we're going to see this histogram again in a few minutes. So what we see here is a depiction of the central tendencies of our sample around a particular variable, in this case the ACT scores. And so what we see is that when we generate the output from a histogram, we also get some other information. We see there's a mean, a standard deviation, and the N. So when it comes to being able to quantify the constructs of central tendency, we have a few different tools at our disposal. And it's great to be able to visualize those with the histogram, but we also want to make sure that we're able to reflect those numerically and to be able to describe what they mean. There is the old adage that a picture is worth 1,000 words, but when it comes to reporting statistics, it is critical that we describe any figure that we utilize. So for these measures of central tendency, we have the mean and the median, and in the book, Field gets into describing mode, but when it comes to reporting on measures of central tendency, mean and median are what we use, what we see. We see the mean a lot, and mean is simply the average of scores or average of whatever is represented in a particular variable. It is important to note that a mean cannot be calculated with ordinal data. So let's say that we've got a Likert scale item which reflects an ordinal scale. We would use the median to report on the measure of central tendency for that ordinal data. The other piece that we see reported that we utilize to help us understand the central tendency for what we're looking at is standard deviation. And so we see this reported as standard deviation from the mean quite frequently. And it just gives us a sense for how tightly clustered around the mean or the central or the measure of central tendency is the sample. And then we also look at some critical values for skewness and kurtosis. So using this data set of the ACT scores for high schools across Kentucky, we see a number of different pieces being reported. We see the N, obviously, of 131, which we saw reported on the histogram. See the mean of 8.2, the standard error of the mean of 0.095, a median of 18.1, the mode of 18.1, which we're not going to get into mode very much. The Field does a good job of kind of explaining and situating mode. Standard deviation of 1.09, the skewness of 0.509, standard error of skewness of 0.212, then kurtosis of 0.420, and standard error of kurtosis 0.420, and the range of 5.9. And it's important when we report on a sample, when we report on some particular aspect of a variable, descriptive statistics are important. I think sometimes we have this tendency, or maybe we see it reported in journal articles, there's this tendency to preference inferential statistics over descriptive statistics. One is not better than the other. They have different uses and different purposes, and we're going to get into those throughout our summer together. So some questions to answer about this data. One, is the distribution normal? And what is the central tendency and variance? So if we look at our histogram again, we can get a sense of where things are. So we've added a line in the histogram to indicate the mean. And so we've got a real good sense of kind of where things are. And so, as I noted, when we ask SPSS to generate a histogram, we do get some descriptives at the same time. And we already had run our descriptive stats, and so we know that our median is 18.1. So if we use these descriptive statistics to get a sense of normality, we've got some information that we can use. And so in looking at skew and kurtosis, and I'm going to break this down a little bit more in another slide to kind of show how these calculations work out. But in calculating or interpreting, okay, what's this skew? To what extent does skew and kurtosis reflect normality? You see that there's this number of 1.96 being utilized, and we use that in calculating our confidence interval. And so I'm going to get to that in just a few moments. So if we so I'm flipping back and forth. So we're going to come back to kind of these ideas of kind of getting where things are. And so if we look at kurtosis and we take the kurtosis and divide it by the standard error kurtosis, we see that it's 0.420 divided by 0.420, which equals 1. That's normal. If we take the skewness, see 0.059 divided by 0.212 equals 2.4, and we get a sense that there is a skew and it is positively skewed. So the central tendency and the variance, we see that the mean and median are pretty close to each other. There's a standard deviation of 1.09 and a standard error of the mean of 0.0954. So we take all these pieces together and we come up with some conclusions so far. Number one, that the sample is slightly positively skewed, and the mean and median are very close, and that the standard error of the mean is much, much smaller than the mean, so the sample is representative and it's stable. That means that it is not highly affected by outliers. So if we put this into kind of practical terms, what does this mean? The average ACT score in this sample of Kentucky high schools is 18. And so we see that, again, if we see this close relationship between the mean and the median, we get a sense that there is a clustering around this number that is very close to 18. And that there are several schools that are skewing the data positively, which means that we're seeing higher ACT scores at some high schools. And so if we think about the idea of probability distributions, and we're going to get into this again in more detail when we talk about t-tests, because that's really when we think about, if we're using a two-tailed t-test, for example, the relationship of where things fall within the normal distribution. So if we think about probability distributions and variance, we see, again, from our descriptive statistics, the standard deviation was 1.09 with a mean of 18.2. 68% of the population should fall between 17.11 and 19.29. The fact that the distribution is skewed does affect this assumption. Only about 5% of the school should be above 20.38 or below 16.02. And the schools that are beyond 3 standard deviations represent the outliers. So another way to think about this or to visualize it is the use of a box and whisker plot. And what the box represents is what's known as the interquartile range, and this reflects that 50% of the scores fall in the middle. So that means that from our sample, 50% of the scores are represented within that box. Notice that there's some dots on the upper end that represent outliers. And so again, these are those data points that fall more than 3 standard deviations away from the median. And you'll notice there's some numbers next to each dot, and for the outliers, those numbers represent the row numbers in the data set from SPSS. And so for this information on box and whisker plots, take a look at Chapter 4 in the field book, particularly section 4.5. So when it comes to error and confidence intervals, there's always error present. There's going to be measurement error that's likely to be an issue, and we're going to get into some more detail on error when we come together during residency week. So the standard error of the mean is also represented as standard error, and you may see it abbreviated either as SEM or SE. And we use that to calculate our confidence intervals. And so you think about that as the plus or minus around a value. And probably not the best example, but we see this when we see polls being reported on the cable news networks. And they'll tell us that 47% of respondents were favorable to the idea of raising taxes to pay for the new park. And then it'll be something, a little piece in parentheses on the screen that says plus or minus 3%. So again, it's not the best example to show how that gets used, but I think that's something from our daily lives that we see. And so the standard error of the mean is calculated as the standard deviation divided by the square root of the sample size. And to see for the equation, take a look at page 54 in the field book, and it's equation 2.8. So to calculate the confidence interval, and this is all about kind of the probability. So what's our confidence that we feel, or what's the probability that we're confident that something's going to happen, basically, or that our sample is representative of the population in the case of these scores. And so for this formula, take a look at page 57 in the field book, and it's equation 2.9. So for a 95% confidence interval, we're going to take the mean, and it's represented plus or minus 1.96. So this is where that 1.96 from earlier comes into play, times the standard error. So from the example of our data set in this video, so our question would be, what is the 95% confidence interval for the example? So if the mean is 18.2, so we would then reflect that as 18.92 plus the 1.96 times the standard error of the mean, which was 0.0954, and that gives us 18.38. And then the lower end would be 18.2 minus 1.96 times 0.0954, which gives us 18.01. So our confidence interval suggests that we believe that the ACT scores of the population will fall between 18.01 and 18.38. That wraps it up for this video. As I said in some of the intro pieces, as much as possible for these videos, and it's going to be interspersed. Some I'm going to go through providing some more detailed explanation of the concepts as presented in the book and supplemented by some other pieces. Others I'm going to kind of walk through some of the concepts in this way by using examples. And let me know if one or the other works or doesn't work for you, and I'll make adjustments as we go. So please provide feedback as you go through the course, and I hope that each video is valuable for you.